Silence. I probably won't have the theme music in because I'm not sure if it's going to be working. So today, guys, it's probably going to be my last of 2 videos. 12-2 we might do in school, we might not. We'll see how much time we got. But we're going to talk about regression today. All right? We've done regression lines, but now we are going to make inferences on it and make confidence intervals on what things can be. Before we get too far into it, I'm going to go to the next slide. So our learning targets, we're going to check conditions to make sure we can perform tests. We're also going to interpret in context. We're going to make confidence intervals and perform significant tests on our slope to see what could be the possible true slope. It's everything we've done, just a little bit different. So what we're going to refer to today, this is straight from your book, is we're going to look at the scatter plot of all the eruptions of Old Faithful in a single month. There's 263 of them. And we have, out of that population, the blue line is our least squares regression line of that beast. All right. So now, a quick review of some things that we know, but we want to make sure we know. So before, back in chapter 3, was it? We had this equation down here, right, where we can give a predicted value given a predicted x. But now here we are using a little bit different notation for when we talk about the population regression line, the true regression line. So we use mean of y, and we're going to use capital B, capital beta actually, and capital beta 1 for the slope. So again, when you see those, we're talking about the population, the true slope, the true y-intercept, the true value of the y. And these were given our sample, these are estimates. An estimate of y. Our samples y-intercept and our sample slope. Okay? So population, sample. Okay? So here are some scatter plots. We decided we were going to go wild, just buck wild. And we took 3 different samples of 15 Old Faithful eruptions. So this was sample 1, sample 2, sample 3. And we made a least squares regression line for each one. And we compared it against the population for the entire month. And when you look at those, it's funny because you see this one has slope of 10. This one has slope of 12.5. This one has slope of 15.7. And then our y-intercepts go from 44 to 39 to 24. So they vary wildly, actually. So given those samples, we're going to be able to do things like find confidence intervals. So what is the true slope probably? What's it between? We can test it against data to see if it is what they're saying. All right. But what we're doing by taking these samples is creating a sampling distribution. Remember when we roll the dice, when we grab out of the hat, and we make our dot plots? That's what the goal is. We're going to take a bunch of samples of size 15. And when we do, we get something that looks like that, a sampling distribution. Okay? We did 1,000 simulated samples if the true slope was 13.29. So we're assuming that the population slope is correct. And then we're running 1,000 simulations of population size 15. And these are all the different slopes we got over those 1,000. Sometimes they're 9, one time they're 18. But usually they're pretty close to what the true population mean was. Which it should be. We use that for our simulation. So is getting a slope of 10 unreasonable? It happens sometimes. 12.5 happened a lot. 15.7 happened a decent amount. So those are reasonable slopes given the population. Notice what this looks like. I think that's on the next one. What does the sampling distribution look like? It's going to be normal, right? Its center is going to be about the unbiased estimator, what we used for the mean when we took our samples. And it's variability. This one's a little bit different. If I can move my face out of the way. Oh, I don't know where it went. So for this variability, this is going to come up again. Our standard deviation of the sampling distribution is actually the population standard deviation over the standard deviation of the 263 eruptions times square root of n. Alright. The good news is most times this is given to you in a computer printout. But we're going to look at this again in another slide. Alright, so again, if we are taking a sample size n from a population capital N, and we know that to be the population's least square regression line, and we're going to let b, little b, be the slope of our sample, then the mean, oh good, my face was covering that. Oh, now it still is. Winker biscuits. There, I fixed it so you can see there. If all that's true, the mean of the sampling distribution should be the same as the population, right? And the standard deviation of our sampling distribution is going to be equal to standard deviation over the standard deviation of our entire population times square root n. Alright? Now it will be approximately normal if the conditions are met, which we're going to talk about. Of course we are. Remember, pause where you need to. I'm going pretty quick. There's a lot to cover. Look at this cool graph. So basically, for any fixed x and responses y, you're going to end up getting a normal distribution. What they're showing is a normal distribution with that as a mean, a normal distribution with that slope as a mean, and normal. These are samples based on your value x in a given line. It's very, I don't want to get too much into it. I'll probably talk about it in class, but it's pretty neat actually. So you're normal at x3, you're normal at x2, you're going to be a normal at x1. Okay? If you were to make a sampling distribution. Now there's something we're going to need. Oh, my face is gone again. It's gone. So how do we know whether or not we can do a regression inference? Well, we're going to look at something called liner. Okay? And that's how we can know whether or not we can make an inference. The first part, oops, see, liner. Oops. Actually, oh, uh-oh, I broke the matrix. We're stuck inside the matrix, forced to play our hand. I'm doing this web-based, that's not good. And now I'm going to go through each one of these in more detail, okay? So if you want to stop and copy this, great. If not, you can wait for the next slide. But remember liner. Linear, independent, normal, equal, standard deviation, and random. So linear is pretty easy. To make sure you're linear, you look at your residual, okay? Whatever, it won't move my face. Alright, so you could, good, you look at it and they're all about around that line, above and below it in equal parts. That's a good linear, we did it, it's linear. Bad, if the residual plot shows a curve and not a random scattering, it is not linear, okay? So we got good, bad. Independent. Check for independence. We're still doing the 10% rule. If the samples are independent, we don't need to check it. But if they weren't independent, we need to go through and see if our sample size is less than 10% of the population. We've done this before. Not going to spend a lot of time on it. Normal. To see if it's normal, you need to look at the residuals and look for skewedness or outliers. Okay? So, A graph of residuals will usually let you know if it's normal. If you have numbers super high away from it or super low, not normal. If they're all kind of scattered around, it's going to be normal. Okay. Equal standard deviation. What that means is the standard deviation at any point on the line is about the same as any other point. So, like a good one, the standard deviation early on in the x values is about the same as later on. This one's bad because the standard deviations are very small and then over time they get larger. So there's something wrong with your model. It doesn't fit the data well. This one fits the data well because they're equally varied at any point. These ones are not equally varied at any point. And random. Was it a random sample? We've done that a million times. Alright guys, go ahead and pause your screen for a second and read this over. Read it, learn it, love it, and then I'm going to go over whether or not we can do it. Okay, so pause it, read it, and then I'm going to go through it right now though. Alright, so Miss Barrett, let's use paper helicopters. We need to see if the conditions are met. So we need to check liner. Okay, and they already gave us this data. Nice. So, let's go through and check. First, we need to check, is it linear? Well, yes. If I look at this, if I draw a line through it, it looks pretty good. And there's not a curve pattern to my residuals. So it is linear. Nice job. Independent. Because we don't have to do 10%. Because we released them in a random order and no helicopter was used twice. So, because none were used twice, we know that each trial was independent of each other and none of them were used at the same time, or two were used for data. Nice. So linear, yes. Independent, yes. Normal. Well, when I look at the histogram, it looks pretty good. There's no skewed or outliers, so it is normal. Equal standard deviation. My spread in the beginning is about the same as the spread at the end, so I would say that that is an equal standard deviation. Okay? It's the same at any point on this about. And lastly, was it random? Yeah, it was randomly assigned to 5 possible drop heights, so yes. We did liner. Linear, independent, normal, equal SD, random. Now, if there's one outlier or little issues, guys, don't nitpick this. It will be obvious that it doesn't work. Okay, it will be obvious. Obvious. And that's actually where I want to end it today. I will do the rest in 12.1b. Thank you guys for watching. Have a great day.